Hello, everybody. Welcome to today's webinar hosted by FRAMOS with the topic of ultra-fast SLVS-EC sensors. Accelerate your high-speed vision design with SLVS-EC. The speaker today is Giuseppe Contini, who is a computer science engineer with over 2 decades of experience in imaging systems, software, and hardware. Over the past 7 years at FRAMOS, he has supported multiple clients by providing custom design solutions from requirements to mass production. He's truly dedicated to research and development, and with that, he has not only advanced the field of computer vision, but he has also contributed significantly to establishing FRAMOS as a trusted partner for clients worldwide. As a technical imaging expert, today he continues to drive innovation and contribute significantly to the growth of computer vision technology. My name is Frederik Schönebeck. I am the Director of Growth, and it's my pleasure to host this webinar today. As for the agenda, we have 20-25 minutes in front of us, where Giuseppe will start to talk about the challenges that high-speed sensors bring and motivate the need for ultra-fast SLVS-EC sensors. Then he will go over to present a number of examples where SLVS-EC sensors are used in specific applications. And then towards the end, he will show how FRAMOS supports its customers by implementing the SLVS-EC high-speed interface into their solutions. And finally, we will conclude the presentation with a questions and answers session. As for the questions, please use the little question mark button towards the upper right corner of the go-to application that you're using. Once you click on this button, you can place your question in written. I will collect those and we will get as many of them answered during the meeting. And in case we are not able to answer all of them, we can follow up offline. With that said, Giuseppe, I hand over to you, and I wish everybody a nice and productive webinar. Thank you.
Thank you so much, Frederik. So I'm Giuseppe. Frederik already did a nice introduction, very nice introduction about me. So I will go through challenges that I see, and we, as FRAMOS, we see with SLVS-EC image sensors and how we solve it. So again, today we will be focusing on image sensor interface. So not camera interface, but is the interface between the image sensor board and the receiving board, which could be an FPGA, SOM, SoC, DSP. There are many of those. So it's edge processing, embedded processing, or it could be as well a camera interface board to stream then to other interfaces. So these are typically MIPI, LVDS, SLVS-EC, and sub-LVDS. It's common names for this level of interface, right? So, but technical people are always following the market or are pushed from the market. And I want to give you a perspective of what is going on from the market perspective. In general, the demand for speed and resolutions grows. So it doesn't matter if it's for frame rate or resolution or for both, maybe. All the applications are increasing in this direction. So high accuracy inspection, for example, of course, you need very high resolution or very fast laser triangulation. 3D inspection needs both. So this is the trend, and we see this trend is moving every year, more or less, in the direction of high data rate, right? And this is the point. So let's have a look. Some Sony sensors, some of the latest Sony sensor. Here it's data rate or payload, actually, and you see the new IMX925 family, which is 24 megapixel. Okay, you say it's not that much. It's already a lot. But if you also consider the frame rate of those sensors, it could be 400 frames per second. It's a huge amount of data when you transmit 24 megapixel at 400 frames per second. Yes, it's 8-bit, but if you go to even 12-bit is anyway a lot of data, right? And you see on the chart on the right also some comparison. So first, what the plot tells you here. It's the resolution to give you some reference to how big are these sensors. And on the y-axis, you see the payload. So what is the amount of data that the sensor needs to transmit to the receiving host? This is an easy calculation. It's a resolution by frame rate by bit depth. Of course, there is some overhead on top of that, but this is to give you in one pictures and tells you what is the tricky point that we are and we can solve with SLVS-EC actually. Which is the new interface, because you see MIPI is very nice, very well accepted, widely used, but is not fast enough. At least a D-PHY at the current version with 4 lanes, you can manage quite low data rate. Even sub LVDS is very well appreciated because it's easy, but it's typically up to 1 gigabit per lane. So then you need to have many lanes, and anyway, you cannot achieve the new image sensor. So this is how to manage such high data rate. So because we are talking about interfaces, I want to give you a comparison of the interfaces itself. So here we have the name of the interfaces, the D-PHY, C-PHY, sub-LVDS, SLVS, which is another variant of LVDS, and SLVS-EC. The plot tells you everything. So the comparison is, of course, is telling that SLVS-EC is the interface for high speed or high data rate in general. They come with different specification, different version of the specification, even other interfaces has, but here is showing how many gigabit per lanes it can be transmitted with the specific interface. So up to 12.5 gigabit per lane is the latest. 10 is also quite new, so that's why I've make it bold in the true version. And here you see also the number of lanes. The plots is showing some real case that I've seen from the sensors, and of course, here 8 lanes at 12.5 gigabit per lane means 100 gigabit per lane, huge amount of data. So that's it. But I mentioned per lane, what that means. So of course, to go to a certain, to transmit the full data from the sensor, one lane is not enough. One lane is one data lane, so it's a pair of wires or tracks, as you want to call. And with SLVS-EC, you can transmit up to 60 gigabits in total, just using 8 lanes, right? So it means 8 tracks, 8 pins on the connector for the data. If you want to do the same with sub-LVDS, to get the same amount of total data rate, you need 64 lanes because you can only run at 1 gigabit per lane. And so this is then converted into number of wires, so 64, because a data lane is made by 2, then you need 64 lanes, means 128 pins. And this is quite complex PCB design that you have to handle. Also because there is the embedded clock. So on SLVS-EC, the data lane is also embedding the clock of the data. So this is a digital transmission, and the time of this transmission is also embedded in the pair itself. On other serial transmission, there is a signal to synchronize all the lanes. So it's one single clock for all the 64 lanes or whatever you have. This means that the time to transmit from the image sensor to the host must be the same for all the lanes. True, we go at a fast at the speed of the light, but anyway, all the lanes run in that way. So this obliged you to keep the pairing of the line, so the length and all the insertion loss, everything, any delay that you put on one lane must be the same on other lanes. This is possible, but with some tolerances. And you see here the small tetragon that tells you the A pattern. So what is the tolerance that you have? If you have a very small pattern there, you then have out of sync between the lanes, and the communication gets broken. So all in all, SLVS-EC is allowing very easy path design and is optimal for fast transmission, because as fast you go, as less margin you have for error tolerances. And indeed, we talk about long cable transmission. This is typically something that sometimes is needed, sometimes not, but also because the length of the distance between the image sensor and, say, the FPGA board, the receiving board, could be even some centimeter or maybe some meters. We need to care about all the components in the pipeline. So connectors, plugs, cable, environment matter. So the systems are very sensitive. With SLVS-EC, and also it's possible to simulate. So there is the models of the SLVS-EC sensor, so the transmitting part that you can put together with the models of all other components of your chain and do the simulation and check if the robustness, so the red square that you see here in the A pattern, tells you how robust it will be your communication. So this can be done upfront with correct simulation. What we have seen is that 1 meter at 5 gigabit per lane seems good enough. Maybe this also depends on the application. Even 5 meter could be feasible. This must be simulated, and the simulation can consider different type of cables. So here you see some example of cables that you can use it. So TSL are very nice for long transmission, and SSL and others can be simulated depending on the real case scenario. Error detection is also very nice, and error correction, this is also specified by the SLVS-EC. So here the sensor, the image sensor, the transmitter part is embedding the CRC code in the packet data, and the receiver part can easily detect any error in the transmission. So this gives you a lot of this allows you to keep under control the safety and monitor the quality of the transmission. And in some cases, you can also correct 1 or 2 errors inside of one block of data. So safety is also a nice feature that you can implement with SLVS-EC. So now I will show you some examples. Here is IMX811. This is huge image sensor. Is a different scenario from 925. Is 24/7 megapixel. It's a very big image sensor, and even the frame rate is very high. SLVS-EC is the only way to transmit data out of this sensor, and also this sensor is even complex because it's so big that it has 4 different interfaces. So not only 1, but 4. You see northwest, northeast, southwest, and southeast. And this also is producing interleaving data between odd lines and even lines, and also between the first pixel and the latest pixel of the sensor itself. So on the FPGA side, this can be managed with different IP core, but also you need some chip to do the combination, to recombine the pixel into the memory and have image reconstructed how this should be. This is another interesting case that we managed. This is an image sensor which is SLVS-EC native that should be connected to the Jetson O-ring. So this is a really embedded system, but the ORIN does not have SLVS-EC input. So how then connect this sensor to the ORIN? And also here, the requirement was I want to have very long cable. We talk about 5 meters. In this case, the data rate were not so fast, not so demanding. So is it possible then to do SLVS-EC to MIPI? And then what we did is also converting MIPI to GMSL. After 5 meter cable length, then we go back with the deserializer GMSL to MIPI, and then the ORIN is seeing the standard MIPI D-PHY image stream, and it can be handled. And also, it's nice, GMSL can handle power over coax, so we remotely power the sensor board as well the motorized lens. This is another exotic or another very interesting, more than exotic. We have seen some SoC does not have a SLVS-EC receiver, but we have the IP core. We can provide the IP core in source, in the format of HDL or Verilog. The ASICs manufacturer can then pull the SLVS-EC receiver core on their own ASICs, then sell the ASICs to the customers, and then the customer can build a receiver board which is natively supporting SLVS-EC as a receiver. And this allows to connect the image sensor board directly to the SoC. So whatever it is, I mentioned we have SLVS-EC IP core, so means that we support what the Japanese Industrial Imaging Association is specifying. So the SLVS-EC, it's a standard, it's a protocol that is specified by the Japanese image sensor Industrial Imaging Association. It has a different version, and FRAMOS is, so this is, in FRAMOS is doing the IP core to receive the data stream, which is compliant to the standard as is specified. So we have 2 versions right now that's supporting the low speed and high speed, and the highest speed at 12.5 gigabit is coming soon as well. So the IP core from FRAMOS is something that you put on the Xilinx FPGA or any other. This could be considered and discussed, and it can receive the bit stream from the image sensor and actually it convert into pixel data into the memory buffer. This is what we do is an off-the-shelf IP core, so you buy and use it. There is a reference implementation. It's independent from the sensor. It's in some way portable to other FPGAs and is available as I mentioned that source code or encrypted, typically encrypted, but all in all, you have seen SLVS-EC is making easy to transmit all of those data, but the implementation of the receiver part and all the technical details that I skipped today are really requiring a lot of design time. So this offers an easy way to save money, do the verification, and also save time, of course, and also be updated because we do new version as soon as the new version of the protocol is specified. Not only, we also provide the reference design and the reference hardware. You see here, the reference design is based on the Xilinx development kit, which is not included, but we offer the latest image sensor with the adapters that are needed to connect, and also a complete example of the camera design, where the SLVS-EC IP core is included, but also we show how to configure the transceiver, configure the sensor, and do some basic image processing that, of course, you can change that. But this is really an example for a quick camera. Everyone can start from here and design their own imaging pipeline. That's all. So we are now at the Q&A session. And what else? I will maybe ask to Frederick if we have any questions from the audience.
Thanks, Giuseppe, first of all. Very interesting, lots of information. Yes, we do have questions, actually a number of them. I'm glad that we have some time to go through all of them. You mentioned that SLVS-EC is an open standard from the Japanese Imaging Association. You have now mentioned mostly Sony sensors. So is this a standard that is exclusively used by Sony, or are other image sensor vendors using the standard as well?
Good question indeed. SLVS-EC it's a standard, and so it's possible that other sensor manufacturer implements their transmission part of the standard in their own image sensor. I have seen at least one sensor manufacturer that is using SLVS-EC recently, and so I expect that more will come, in special in the range of, as I mentioned, high data rate and high resolution.
Mm-hmm. Okay, thanks. A couple of more questions regarding the IP itself, the IP core that you were talking about. Mm-hmm. Do you have a rough estimate on the size of the IP on the FPGA and how it compares to other interfaces like, for instance, CSI IP?
I don't have a comparison, side-by-side comparison, but our IP core is, I don't have in mind how many lookup tables and memory blocks it is using, but I know it's very well optimized. We can deliver, because this is in the data sheet of our reference design, and we show, depending on how many data lanes or which functions are we using, we provide exact estimation of all of those typical reference, which are lookup table, flip-flop, memory blocks, and so on. So ECC and CRC requires more resource on the FPGA, true, mm-hmm. But we can share this table. I think is also publicly available, our data sheet, and there we can we show this resource exactly, exact number, yeah. But I don't have a comparison with D-PHY. The question is maybe different. So D-PHY and SLVS-EC are two different things. So the sensor itself cannot transmit on D-PHY as much data more than what D-PHY is allowing. So that's why it's not that one is better than the other from resource FPGA perspective. This is a new step in imaging. If we want to go to high resolution, high data rate, we need to do a new step in the interface domain as well, as also in the processing domain as well, because, okay, I'm receiving the data, then I have a huge box on my CPU, and I need to process this data, and I have much less time to process it, because, of course, the frame rate is high. So it's all a complete new level of imaging systems.
Good. Then let's stay on the IP core for a little longer. What are the supported pixel data formats of the FRAMOS receiver IP?
Mm-hmm. That's also a nice question, a good question, because it allows me to say that we support all the pixel format that the sensor is supporting. So because the IP core is a sensor independent, we just need to configure the sensor in the sensor mode, and we receive as the sensor is transmitting. So we don't have limitation on that regard.
Okay, thanks. I think that makes it clear. Another question regarding the functionality of this receiver IP core. Mm-hmm. We have a question that sort of goes in the direction of, is it the IP core that you are describing? Is this only the receiver part, or does it also cover other parts of a camera pipeline? Especially also the ISP part of a camera pipeline. Mm-hmm. And also, if not, then how can these different IP blocks be connected together?
Yes, again, good questions. Nice that we receive all of those good questions. The reference design is showing an example of the pipeline. The IP core itself is only dedicated to manage the receiving stream. So it's converting 8-bit, 10-bit encoding of the from the sensor into pixel data. And then the reference design is showing how we do, for example, demosaicing. But everyone can then replace that block that we provide, like an example, to any other very complex or very long pipeline out of that. So there is a memory buffer where the user cores can get it out of the data and do whatever processing is needed. But we focus only on the receiver part. So SLVS-EC is like PCI Express, and in some way you have to decode the stream because the embedded clocks is what is making the difference, right? So, and you really need to handle the transceiver and all the combination I've shown also from multiple interfaces, and this is what the receiving IP core is taking care.
Okay, great. I think that's clear. Another one regarding simulation. Is there a recommendation you have how to simulate the SLVS-EC links?
Yes, so simulation is first of all requires all the models of the chain, and there are tools to do this simulation, and the transmitter part and manufacturer is providing the model of the transmitter, IBS model, for example. Then you have to collect the models from the cable suppliers, the connector suppliers, the FPGA suppliers, and put all together into the simulation tool. This activity is very advanced, I have to say, but the good point is that when there is a demanding application and you really need to do simulation upfront, simulation is now also well known as digital twin, right? So in some way we can predict something, and this is definitely possible. Requires dedicated effort on this, and sometimes we also have seen a customer that they prefer to try, right? So really, because there is the reference design, they can then use a different cable maybe and build different interfacing and make their own measurement on that. But of course, when you go on the field, maybe in an industrial environment or doing some extra tests, you can maybe have the need to simulate a different use case scenario. In this case, the simulation is very, very useful.
Great. Then one last quick question. If a sensor comes with version 2 of the SLVS-EC interface standard, and we connect it to a version 3 IP core, a receiver IP core, does it run faster? Is that possible at all?
Unfortunately, no. Means that the version 3 of the protocol is capable to transmit up to a certain amount of data, but you can run lower. But if the transmitter is lower than the receiver, of course, the receiver is adapting to the transmitter. So it means that the main driver is the image sensor, is the physical interface on the image sensor. So depending on the transmitter. What is good is that, and the IP core in the version 3 is backward compatible. So you don't have to run it at the maximum speed, but you can configure the receiver part to different, even to version 1.2. So no matter there. Yeah.
Great. Thanks, Pino. I think we covered all the questions, lots of questions, great questions. So it seems the information was very well received. I'd like to wrap the webinar up at that point. Thanks everybody for your attention. There will be a few more webinars coming soon. The next one being on June 11th, where together with Sony, we will speak about new advancements in time of flight and event-based vision. Then later, on June 30th and July 1st, FRAMOS will speak about what is good image quality. Actually, a very good topic with no clear answer, I would say. In July 10th, we will have a dedicated session on high resolution sensors, integrating 100 plus megapixel sensors, where again, we will speak about the IMX811 that was already shown by Giuseppe earlier. And then finally on July 24th, together with Sony, we will focus on the Sony Pregius S global shutter sensor series and the latest evolutions there. There will be also more topics to be covered in the second half of this year, but this is an outlook for the next month. Thank you, everybody, for joining the webinar, and hope to see you soon in the next session. Bye-bye.
Thank you, everybody, for listening. Bye.